multiple CTOs and senior. He has held multiple CTO and senior executive roles across global operators and leading technology vendors. And previously, he played a key role in scaling Metro PCS and supported its $33 billion merger with T-Mobile through product strategy, market execution, and business transformation. In addition to his operating leadership, Dr. Ashrafi has served as managing partner at a private equity firm, founded technology and software ventures, and contributed through advisory and board roles. He holds a PhD and advanced degrees in engineering and science, and is the inventor of 140 patents and author of 85 referred publications. So this is the first time Onefinity Fujitsu is a sponsor of my conference. So, and he will be talking today. Is a very interesting topic. AI is ready, but network is not. Okay. So with this, let's give a big hands to Dr. Ashraf.
Can you all hear me? All right. It's after lunch. All of us are a little sleepy, but what I see here is that most of you come from computing industry background. I'm coming from a networking background, okay? And when I say networking, I oversee all of the optical gears, all of the networking, all of the services, and so forth at Fujitsu. So, but the thing is that you guys have done a tremendously good job of scaling up and scaling out, and even a scale across at the Ethernet IP network layer. What I'm trying to do is to really bring down to the physical layer, optical layer. And so if you look at what you guys have done, is you have evolved computing industry a lot faster than what we have done on the network side. So it is by 3 orders of magnitude faster. I'm going to show you some data to see why computing is no longer the bottleneck. The network is becoming the bottleneck now. And the industry has to pay attention on a scale across at the physical layer. What I'm talking about, optical scale across. We have folks here from Broadcom and maybe NVIDIA tomorrow. They have done a lot of good work in a scale up and a scale out, even at the optical layer. But for a scale across, if you look at NVIDIA, they have a Spectrum XGS, but those are network level solutions. So what I'm trying to say is that AI is ready, but network is not, and the ecosystem has to pay attention to that. Does this have laser as well? Okay, this one right here. Okay, it's dim, yeah. So if you look at the ecosystem, the problems we have is that the hyperscalers and the model owners like OpenAI and Anthropic, they all have compute issues. Like they exhaust their compute capacity and they need to leverage some other compute infrastructure. In many cases, they go and leverage new clouds, okay? There are more than 210 new clouds already launched data centers, and they offer GPU as a service. To be honest with you, GPU as a service is a commodity business, it's not a good business, okay? So what I'm concerned about is that if they do not utilize the GPUs that they bought, okay, it would be problematic for them. They have to show return on investment, okay? And what I'm telling you is that other than some of the top ones like CoreWeave and Nebius and Crusoe and others, most of them have only about 30% utilization on their compute. So that is, the compute doesn't find its way to their infrastructure. So they have a lot of GPUs sitting idle. And that's a big problem. Now, the other thing is that, as I said, NVIDIA, Broadcom, and others have solved the scale up, the scale out, even the scale across at the network level. Now, the scale across at the optical level requires more attention. And so if you look at the new clouds themselves, or even the hyperscalers, they have data centers. One owner has multiple data centers, and they need to connect them. They need to stitch them together so that they have a compute continuum, all right? And that's one issue that they have. The second issue is that, as I said, there is stranded compute issue, which is a bigger issue for them, especially the ones who have not really done a one-to-one interconnection to hyperscalers. Some of them have done that, like CoreWeave and Nebius and so forth, but there are a lot of them that have not done that yet. They are betting on enterprises, and enterprises are fragmented and so forth. So it's very difficult business to be in, especially because if you look at the way some of these companies are operating, is that if their annualized net income over their CapEx investments is not a good ratio, like if you even look at Oracle, is at 8.4%. Okay, if you look at Microsoft, is at 40%. So when there's a credit crunch, Microsoft, Meta, Google will survive the credit crunch, but the ones who don't have a good ratio of this annualized net income over CapEx will struggle. So I do see that AI is definitively a bubble to me, okay? But what that means is that, first of all, if there were no bubbles, we would still be in caves, okay? We need bubbles, okay, for innovations to happen. But the thing is that when we say AI is a bubble, we mean that there will be booms and busts. There will be many companies who would be on the boom side, many companies who will be busted, okay? That will happen because credit crunch is definitely coming based on what is going on with the top 3 economic powers in the world. All right, so now I said that compute is racing faster than the scale across interconnect. That is, my view is that the bottleneck is no longer compute side. There's tremendous amount of compute power already available, especially with all these new clouds. In fact, hyperscalers are thinking, well, there's a cheap GPU resource. Why won't we use them, right? So that's why they're trying to interconnect to these new clouds to leverage their infrastructure. If new clouds go out of business, hyperscaler would still be around, right? So that's what they're doing. The thing is that it is growing, the compute is growing 3 orders of magnitude, 10 to the 3 order, faster than interconnect. So that's where the bottleneck is the interconnection. And therefore, we can no longer look at network as a passive plumbing anymore. It is a critical component of stitching together and creating a compute continuum. And the reality is that the AI performance is now dependent on bandwidth, latency, distance, jitter, path control, congestion. All of these things matter for inference and training. And that's why at Fujitsu Onefinity, we have created an optical NIC that I'm going to talk about today, where you can sustain a very, very high throughput over very long distances. I'm talking thousands of kilometers, okay? But in order to do that, we have to bypass some of the protocols, and at the end, we have to do certain things, and I'm going to talk about that today. Now, how do you solve the new cloud stranded compute? What that means is that the new clouds need to broadcast somehow what their compute capacity is almost in real time, so that the hyperscalers and other new cloud, other model owners, when they exhaust their compute capacity, they can find these infrastructure resources. The current data center interconnect is too static, too rigid, and too one-to-one. And what I'm trying to do is to make that to be many to many, okay, dynamic and flexible. And that requires a lot of things at the control layer, at optical layer that I'm going to talk about. So with that, I will show you this graph that you can see compute is growing much, much faster. This is not my slide. There's a reference here. And even this one is for a scale-up interconnect. Now imagine you go to a scale-across interconnect, it's even worse than this, right? So 3 orders of magnitude difference in terms of evolution. That's why we have the bottleneck in the network. Compute has grown much, much faster. So why do I say scale across is not the same as data center interconnect that we know? If you look at the telco industry, they have created all these interconnect, but that interconnect is not going to work for the AI era. That's why we need to look at optical scale across. That is, we need to be able to stitch these distributed compute, so that you have a holistic compute continuum. Because if you look at the original data center interconnect, they were mostly put together for disaster recovery, storage replication, and workload mitigation. That's not what we need for AI era. You need a lot more dynamic and systems that can communicate, and the memories and the compute infrastructure be able to be shared between data centers. And therefore, you can imagine what I'm talking about is almost like extended backend, right? Like imagine that you can scale out with a very high performance. That is almost the performance of what you have within the data center. Can that be done between data centers that are thousands of kilometers away from one another? Now, we cannot solve for the speed of light, okay? So that we cannot solve for, okay? So you do have that latency. But there are other things. For example, I was in a conference in Dallas, and they are trying to build this network between University of Texas at Dallas and other campuses with hollow core fiber, where you don't have much chromatic dispersion. You get a very, very high throughput. So that network is planned to be put together. Therefore, if you look at training, it depends on utilization, collective communication, parallel, approaches for different models and whatnot. And then inference depends on latency aware, routing, KV cache, low latency, predictable time to first token. So all of these things matter. And when you go to the optical layer, try to do scale across at the optical layer, you're trying to solve some of these problems, okay? Now, what I have termed is a fluid interconnect, meaning that the whole compute is fluidly going across the data centers, okay? That fluid interconnect creates a programmable X-aware fabric. And what do I mean by X-aware? I mean that it should be traffic aware, it should be distance aware, It should be latency aware, jitter aware, network aware, performance aware, and even tier aware. What does that tier aware mean? When you're prompting, let's say with Gemini as a large language model, you can do your prompting using, fast, pro, or thinking. Those are different tiers, okay? Based on these tiers, you should be able to have a network that fluidly connects everything based on all of those things. So a scale across interconnect is no longer plumbing, okay? It is the first order system design variable that determines viability at the scale. That's what I'm talking about. All right, so now I have a measure, and my measure is no longer bits per second, is no longer bits per second per hertz of a spectral efficiency, but it's bits per second per hertz per meter, per latency, per prompt, per query, per token, per watts, per dollar. That's the measure. Now, can the ecosystem double that every 2 years? Well, for Fujitsu, I'm talking about ecosystem, guys, because we are not playing, although Fujitsu has a large language model called Takane, okay? But my communication group is mostly working on this side. How do you increase bits per second per hertz per meter for latency, with very low latency, okay? I'm playing on this part. The rest of the ecosystem has to play on the other parts, okay? So for example, if you look at MIT, there's a group that is working on context window. I mean, the biggest problem in the AI ecosystem, one of them is the context window. It's about 1 million tokens, right? What they have done is that they partition that, put some of it outside, and they go through some recursive, they call it the recursive language model. Say is a different. So they're trying to solve that part of the equation. I'm trying to solve this part of the equation, but hopefully, can the ecosystem double this every 2 years, almost like Moore's law? This is what the ecosystem needs, okay? But it requires a lot of technology to be able to do that, especially the last part of it, $sign, right? To do it at the very, very low cost. So here's the situation. There are a lot of new clouds, as I said, about 210 of them. There are a few hyperscalers on the top, and currently they are trying to do, and they are doing one-to-one connection, okay, interconnection. This is what's happening. But what I'm trying to say is that there are a lot of them that have a stranded compute problem. The compute doesn't find its way to them. So what I'm thinking is something like this, where there is a neutral hub, and this neutral hub could be a telco, could be AT&T, Verizon, or NTT Data. It could be a colo, like Equinix, right? It could be even a CDN type of company, like Akamai, okay? This neutral hub could potentially select. They don't need to buy GPUs. The GPU, there's tremendous amount of GPUs down here, okay, by neoclouds. They don't need to buy GPUs. They need to facilitate this interconnection so that when this new cloud has compute capacity and no one is using it, when the hyperscalers go out of exhaust their compute capacity, it could find this guy, right? But how could that happen? Well, these guys need to broadcast their compute capacity, how much compute capacity is sitting idle, right? So there got to be some sort of a client software over here that would do that almost in real time, and these guys find their way over here. The other thing is that imagine two new clouds have the same compute capacity sitting idle. So how would that neutral hub select which new cloud it has to route it to? Well, it would be based on latency. It would be based on congestion. If you want to go through this path, you may use Lumen, you may use Zayo. You know that NVIDIA is now purchasing a lot of dark fiber, right? They realize that they need to go down to the optical layer. Okay, so I want to zoom in here and try to show you, first of all, this neutral hub is not just one. There could be many companies trying to play that role. As I said, Akamai could do that. Equinix can do that. What Fujitsu is doing is building the technology enablers for the neutral hubs to flourish. So I'm going to zoom in here and show you what we do with our SmartNIC, optical SmartNIC. So take one hyperscaler and one neocloud. All right, so, or take one hyperscaler that is trying to connect its own data centers, okay? So what we do is that here, what we are thinking to do is that we have our SmartNIC that can traverse a very long distance with sustaining a very, very high throughput. But somehow we need to kind of hand off the traffic to this data center. So this is one possibility that we can do. Now, if we do not use our optical SmartNIC, we have shown that there's a degradation as far as you go, as you increase the distance, the throughput goes down rapidly. However, in this side, if you use the SmartNIC, what happens is that you can sustain the throughput over a very, very long distance, as you can see. Okay, so now you could do the same thing with the neocloud. This is one owner trying to connect its own data centers, okay, with a very, very low latency, high throughput, long distance, okay? Or this case, where the hyperscaler is trying to connect to the neocloud, right? But this part requires some sophistication that we would be working with some of our partners to fix that. But ultimately, we need to really, we need to really go through this far distance. All right, so now, what is it required? Well, we would have, to be able to do this, we would have agents, application layer, we would have network layer stuff. We have invested in a company called Arcus, which has, you know, AI routers, I would call them, AI network fabric, they call it. They have really tried to disrupt the market with their AI type networking components. So they have inference-aware engine, they have policy-based steering, they have agentic orchestration, they have all of these things that are needed. And then at the optical layer, this is all Fujitsu, because we have been doing these optical stuff for 5 decades in the telco industry already. So now, what you can see here is the convergence of compute and networking, and that is our SmartNIC, where we would have the pluggable units, 800 gig pluggable units that go to that SmartNIC, and it has a FPGA where you have, you know, function integration is programmable. But ultimately, what that does is that it sustains a very high throughput over very long distances. All right. So there's a transformation happening in the industry, and the transformation is the following. It's going this way to ultimately connect these data centers almost like an extended backend with a very, very high throughput. All right. So as I said, the scale out, the scale up already solved. The scale across also solved at the network level. What we want to do is to bring it to the optical layer. Okay, that's the challenge we have, and that's why we have developed this optical NIC, so to speak. So what is the challenge? The challenge is that the latency accumulates across multiple protocol layers. As you go up on the protocol layers, latency accumulates, queuing and buffering introduces jitter, and maintaining throughput over long distance is difficult at the scale, and performance tuning is complicated for both deployment and operations of the network. And adapting infrastructure to new network load requires redesigning the entire network stack, which we don't want to do. So what do we want to do? We want to build something that does the following. It has a lower latency, lower jitter, long reach throughput, okay? Simpler deployment and use case flexibility. And that's what our SmartNIC does. There are other advances. They are at research level. I don't know if you guys have heard about these new property of photons that have some sort of a helicity or twistedness. I don't know how many of you have heard about that. But what it is that you can twist the photon with some orbital angular momentum, and each of these states are orthogonal states, quantized. So you can use them like wavelengths. So you can encode information in this twistedness. But these are at the research level. I have invested a lot of money at University of Southern California in being able to transmit 100 terahertz per second throughput over fiber, which meant that I used 6 of these helicity states plus 64 wavelengths in DWDM, and we were able to do 100 terahertz. So there are a lot of research activity, even hollow core fiber. Those are things that we are working on and so forth. But those are at research stage. Not until it gets to the commercial market, you would not see the advantages of those things. But at least for the SmartNIC is a commercial product that we are doing a lot of proof of concept already. So the reason we can do this is because we take off a lot of the handshaking happening in the protocol. We just take them out and make a very lightweight approach. And that's why we can sustain the throughput for very, very long distances, okay? So this is the NIC, okay? Agile protocol implementation. Right now is 800 gig pluggable that goes right here. We are building a 1.6 terabit per second pluggable unit. Obviously, it does a very good job of offloading the things that are not supposed to be on the compute. You offload those function, network function off the compute part. This is the way we basically connect the different data centers using this SmartNIC. But then when it gets over here, you still need the networking functions and protocols. So that's why we need to do some work once we get the traffic to the data center. We have to offload it to the data center. So this is what you see here. This is the 800 gig solution that goes right in there. That's the SmartNIC. Coherent optics. And of course, it has FPGAs right now that we can program it for different use cases and whatnot. This is just to show you the throughput as a function of the distance for different block sizes. And also you can see that sustaining that throughput for long distance. These are all measurements over different block sizes. And also we have done that on latency. You can see that latency, it has a very good performance on latency. You can almost imagine that when you go from a scale up to a scale out, you're losing some performance, right? Because of the distances, because of everything else. Now, if you go a scale across, of course, you're going to lose performance. But can you get as close as possible to the performance of a scale out? Okay, for that to happen, you need to have an extremely high throughput over long distances. And that's what we are trying to solve for. So the way we do it is really a strange way of doing it. If you look at the current, traditional standard stack, this is the TCP/IP, and you can see the RDMA type stack here. What we do is that all of this we don't need, so we take it out. Okay. We take it out. And when we do that, we would have a very simple way of doing this high throughput over long distances. Okay, so basically, if you look at all these protocols here, we bypass all of those. Okay, that's how we achieve that. But when we get there, we have to do something because you have to do multitasking, multi-tenancy, and all of the network functions has to still happen at the data center that we need to. But being able to go very far distance with a very, very high throughput has been a problem in industry, and that's what we have solved. Now, these are some conceptual diagrams where if you look at Broadcom solutions, which is great, we can still leverage that. We put it here and we go long distance. It requires some work, okay, but this is possible to do. We can go over hundreds of kilometers this way, okay? Similarly, if we use NVIDIA, Bluefield, ConnectX, scale out here, we can bring it here and do the scale across, okay? So that is potentially possible, but it requires some work to be able to do something like that. And then we have been doing a lot of proof of concepts with all of these agencies that you see in Japan. And we are trying to do similar things in US. And therefore, we have a lot of in progress proposals with all of the top ones. Down here, we would like to kind of work with the ecosystem to really pull that off. So this is my final slide. That is looking ahead. There's an ecosystem forming around us, around Onefinity. And together we are turning the vision of distributed AI infrastructure into a new reality. I was at a conference just 2 days ago where NVIDIA folks were there, and they were asking me to see if we would support their NVQ link, which is really connecting GPUs, CPUs to quantum processor unit. It was a reference architecture to be able to do that. I just saw a poster there of the lady here that I saw. There you go. She was doing a very sophisticated Hamiltonian operation, a time-dependent Hamiltonian with some quantum circuits and simulating it on classical computing. And how you do that, it turns out that for nitrogen, just to find the ground state of nitrogen, she was telling me that it has what, 10 billion? Or, yeah. A combination. It's very, very sophisticated. So what she was trying to do was to reduce the Hamiltonians and diagonalizing it. It's very sophisticated what she was doing. But the point is that a lot of those things may work in here when we have this reference architecture that NVIDIA is talking about. I don't know what their use case is because, you know, when you are close, I don't know why you need such a high throughput between GPUs and quantum processing unit, but there must be a use case that NVIDIA is looking for. Anyway, call for action. I'm inviting the ecosystem partners for a proof of value to be able to do a very long distance optical interconnect between data centers where you could use Spectrum-X, XGS, at the network level, but then we want to do it also at the optical level with a very low latency and high throughput over long distance. I pause here. Thank you.
Let's give a thanks to Ashrafi. Thank you. We have time for questions. Yes. Please use the microphone. Click that. Yeah.
Hi, very interesting work. Two questions. First of all, with this slides, how to test on your test bed? Do you have any open test bed for researchers to access?
We do. We do. So if we get, partners to do a proof of value, we don't do proof of concept because we have already done proof of concept. What we call is proof of value. So if we find partners, we will provide all of the test bed to do that. Yeah.
Okay. So second question is about you have a one technical slides discussing the XRDMA. You said you remove everything in the in the other one. So I'm curious, like how you are able to handle like packet loss and retransmissions, flow control, everything like that.
Okay, so that's a good question. There is a verb like, okay, where is that thing? Let me just bring it up. There are some things in here and some things on both sides, but we are trying to take off as much as possible that is introducing, like if you look at TCP/IP, you want to acknowledge back and forth, a lot of handshake. It introduces a lot of latency. So we take off things that we can take off, okay, and we have, so that we can go direct all the way. But there are certain things we would need to keep in there. Yeah.
There are two questions on the chat. Let me read it. You can read it. I think, how power hungry are those optical modules to reach these high distances?
Okay. Well, actually, we do have some data on that. I don't have it here. They are not very power hungry. However, for long distances, you have to, you can't do anything about the laws of physics, and you got to go the distance, right? All I'm saying is that any protocol in the middle that is causing latency or other things, we take those off, but they're not as power hungry as you think.
Yeah, then there is another question. Have you looked at internet exchange points as a possible way to structure connecting compute infrastructure to customers, or is a fundamentally newer model required?
There are a number of exchange companies who actually, by the way, just so you know, Wall Street has already made a futures contract for compute. So you can almost go buy compute and say, I want the compute in October. Okay, so there are exchanges that do a lot of the transactions, but the network layer connectivity with that neutral hub is a separate thing. So yes, we have looked at a lot of possibilities, but we think that there are potential. For example, if you look at Akamai, for example, Akamai has about 4,400 data centers, and there are edge data centers. And they want to convert all of them to AI data centers, okay? So they could be a classical partner to play that neutral hub in the middle, connecting and facilitating these connections. Yeah, so we are trying to only do the technology enablers for these neutral hubs. We're not going to be a neutral hub ourselves, but we're going to help others to become one.
There are many questions. So let's see, whoever goes might be.
So so just looking at this chart here, going off of what Dr. Liu had mentioned earlier,
Yeah.
or his question earlier, sort of most of these intermediate transport and aspects for TCP/IP, VERB, et cetera, are there partially for reliability and say redundancy checking and stuff.
Yeah.
How do you, if you're bypassing all this and maybe I'm just looking at it naively, it seems like it's getting overlooked. So like how does your hardware guarantee reliability and insurance of like in-order delivery, stuff like that?
True. Okay, so for a one-to-one connection, okay, you can actually bypass some of this with not much degradation in terms of performance. Yeah.
Okay, I must have missed that. Thank you.
Yeah.
Charles and yeah.
I was going to ask, what is the primary source of bandwidth degradation across the link? Is it just
there are two parts. One is chromatic dispersion, which means that every wavelength, because of the index of refraction of the fiber and the way fiber is built, and that's a material science of the fiber, different wavelengths propagate with different speeds. Okay, so that's a chromatic dispersion that would impact. The other one is the actual waveguide itself, that is the fiber itself. So that is fixable. So because there's nothing you can do on the material science part of it. Although, as I said, for example, hollow core fiber, there's no core, you can reduce that. So you can actually improve a little bit on that. But yeah, these two would impact the bandwidth.
And the effect though is a packet loss? Is that what it is? Because you're transmitting across there, or is it just like a fundamental property of the wire that the wire is less bandwidth? Is that where I'm going? Like, or is it just that when you have experienced the chromatic effect, that you lose a packet and that keeps your BDP less than the theoretical BDP of the link?
As you go far distance, of course, of course, everything also depends on the modulation, right? The so if you use QAM modulation, as you go up to higher orders of modulation, you can transmit higher throughput, but then the distance there, you need much higher signal to noise ratio. You see what I'm saying? So if you want to increase the throughput, and you go to higher orders of modulation orders, then your distance is going to shrink. So in order to keep both, you have to do something else.
Okay. So I think there are two questions. Shoham, you had a question. Please press the.
Yeah.
Okay. So two questions. One is, since you travel over quite a long distance, do you have hardware level encryption built into these NICs, or do you plan to do so?
Encryption?
Yeah.
Yeah, we are working on a lot of encryption, including, the post-quantum cryptography, kind of PQC type encryption. Yeah, and then there are other encryption at different layers of the protocol. Yeah, we
Okay. And the second question is, could you elaborate a little bit about, on a slide you said that at present there is not enough good routing, dynamic routing based on congestion and network
at the
situations
optical level.
at the, oh, you mean only at the optical level? Okay.
Yeah, optical.
Okay, that-
See, I think my view is that Broadcom and NVIDIA have actually solved the scale across at the network level, and they've done a great job.
Right.
What we are trying to do is that can be extended to a very, very far distance at the physical layer. In fact, we have another talk on the scale across from Broadcom, right? Right after this. So, yeah.
There was one more question on that row. I don't know. Any? Yes, go ahead. Please press that. Yeah.
My question is there any gain from the latency side of the connection of DCI itself, or the
Yeah, there's a
latency gain?
latency improvement. Yeah, there's a chart for that. Let me see if I have it right there. This is important for inference because the time to first token for inference is important, and that's latency dependent.
But from my understanding, the light speed in the fabric is fixed. How can you get latency gain?
That's right. You can't do anything about the physical laws of physics. You can do on the protocol latencies.
So that's my understanding. So your lane is from protocol side, but the protocol side is nothing about the connection. It's about your endpoint protocol, transport protocol.
Yeah,
part of
we
lane.
just
Yeah.
take off those protocol that are introducing more latency.
Yeah, actually, the same thing applied to DCI and not applied to DCI, DC scale up or scale out. You will get the same kind of gain, right? That's my understanding. If it's not applied to DCI, even you apply to DCN, scale up or scale out, because that's the protocol layer gain on the endpoint. So anyway, you will get the gain. Is that the case?
Well, no, what we are trying to do is to go from one point to another long distance, offload the traffic over here, and then you can add certain protocols to do some of the things at the end point.
Yeah, that's endpoint latency gain. That's not the latency in between the connection.
That's right, that's right.
Okay, okay,
Yeah.
understood. Thank you.
Okay, I think we had a lot of questions. People are awake after the lunch. That's good.
Thank you.
Okay. So let's give a big thanks to Dr. Ashrafi.
Thank you.
So next.